Hello everyone, in this video we are going to discuss the two numericals based upon the irrigation efficiencies. So let's start. First of the problem, it says the depth of penetration along the length of a border strip at points 30 meter apart were probed. Their observed values are 2, 1.9, 1.8, 1.6 and 1.5 meters. Now what you need to calculate is the water distribution efficiency. So let's say if this is a border strip that I'm drawing at which there are different points. So in total we have been given 1, 2, 3, 4 and 5 points. So let's say this is the first point, then this is the second, then third, then fourth and this is the fifth one. The distance between the first and the fifth point that has been given as 30 meter for this particular border strip. Now the depth of penetration, the depth up to which the water has penetrated at first point, that is 2 meter, at second point it is 1.9 meter, at next point it is 1.8 meter, then 1.6 meter and then 1.5 meter. That means it is continuously decreasing. Now if we want to calculate the average value, so the average value of the penetration, or that we call as the mean depth, that will be the average of all of these values, that is summation of 2, then 1.9, then 1.8, then 1.6 and ultimately the 1.5 value, and after summing all of these values it is to be divided by 5. So this gives us the value of 8.8 divided by 5, and that is equal to 1.76 meter. That is the value of the mean depth. Now we need to calculate the deviation of each of the value from the mean depth. Therefore deviations from the mean value. Therefore for y1 value, that d1 value, the small d1, that was 2 meter and the average depth is 1.76. So we will take the mod value so that we are getting the absolute deviations. We are not concerned with the positive or negative sense. We are concerned with the absolute deviation from the mean value. So that is representing the mod value. So the first deviation, that will be 0.24 meter. Then similarly for y2 it will be 1.9 minus 1.76. That will be equal to 0.14 meter. Then for y3 it is 1.8 minus 1.76. That will be equal to 0.04 meter. Then y4, that will be equal to 1.6 minus 1.76. That will be equal to 0.16 meter. And y5 will be equal to the mod of 1.5 minus 1.5 minus 1.76. So that will give us the value of 0.26 meter. Now these are the absolute deviation for each of the watering at the mean level. These will be the absolute deviation of each of the penetration depth from the mean depth of the penetration. Therefore average of these deviations, that will be equal to y, and the value of it will be calculated as the summation of all of these values and taking the average of that. So the first value, that was 0.24, then 0.14, then 0.04, then 0.16, then 0.26 divided by 5. Therefore, value of this y will be 0.84 divided by 5, and that gives us the value of 0.168 meters. Now, the water distribution efficiency. Now, this water distribution efficiency, that is written as 1 minus y upon d, and to calculate this value in percentage, we will multiply it with 100. So this is 1 minus this y value is 0.168 and this d value is 1.76. So from here, if we solve this, the value that we get for this water distribution efficiency, that is 90.5%. So that is representing the uniformity coefficient. That means how uniformly the water has penetrated throughout the depth of the throughout the width of the border strip. This completes the first problem. Moving on to the next one. Now it says that a stream of 130 liters per second that was diverted from a canal. Let's say this was a canal which was flowing and we have diverted a stream. So this stream is having the discharge value of 130 liters per second. It was diverted from a canal, and out of that 100 liters per second that were delivered to the field. That means out of this, let's say there is certain other branching which was done, and after that ultimately when it reached to the field, the water which was supplied, that was having a discharge rate of 100 liters per second. Now the area which was irrigated, that was of 1.6 hectares. So the area irrigated, that was 1.6 hectares in 8 hours. The effective depth of the root zone, that was 1.7 meter. That means if we look at the crop level, this is the root zone of the crop. So the depth up to which the water was stored, that is 1.7 meter. The runoff loss in the field was 420 cubic meter. That means the water which has lost because of the surface runoff, that is having a volume of 420 cubic meters. Now the depth of water penetration, that varied linearly from 1.7 meter at the head end of the field to 1.1 meter at the tail end. Available moisture holding capacity is 20 centimeter per meter depth of the soil. That means it can hold currently the 20 centimeter out of 100 centimeter depth of the soil. We need to determine the water conveyance efficiency, water application efficiency, water storage efficiency, and the water distribution efficiency. Now it was given that the irrigation was started at a moisture extraction level of 50% of the available moisture. That means whatever amount of moisture is available, when that level has depleted to the 50% of the value, then the irrigation was started. So one by one we will solve for all the types of the irrigation efficiencies. So starting with the first one, that is the water conveyance efficiency. Now this water conveyance efficiency, that is represented by this eta C, and that is equal to water water delivered to field divided by what amount of water was supplied. So water supplied into canal at the head. That is how we calculate this water conveyance efficiency. Now we know that the water which was delivered onto the field, that was having the discharge rate of 100 liters per second, and the water which was supplied into the canal at the head level, that was having the discharge rate of 130 liters per second. So placing both of these values, this will be the water conveyance efficiency, and for calculating this value in percentage we need to multiply this ratio by 100. So if we solve it, we get the answer for the water conveyance efficiency, that is 77%. That means out of the total water which was supplied into the canal, 23% has been lost because of the evaporation and the percolation which has taken place during the transmission of the water. Now the second type of efficiency, that is the water application efficiency. That means we need to calculate the amount of water which has been applied exactly to the crop. So for that, this water application efficiency, that is denoted by eta A, which is the ratio of water stored in the root zone of the plant, and that is during the irrigation, divided by the water which was delivered onto the field. That means out of the total amount of water which was supplied onto the field, how much exactly has been applied to the root zone of the crop. Now in the given problem, it was written that the water was supplied at the rate of 100 liters per second for 8 hours. Therefore, quantity of water which was supplied that will be 100 liters per second into 8 hours, converting it into minutes, then converting it into seconds. So this second unit will be cancelled out, and if we calculate this value, that will come out to be 2880 into 1000, that is in liters. Now to convert this value into the standard unit, that is cubic meter, this value will be 2880 cubic meter. That is the standard conversion from the liters to the cubic meter. That is 1 cubic meter, that is equal to 1000 liters. Now this was the amount of water which was supplied onto the field, or that can be written as delivered onto the field. Now out of this water, the runoff losses that has taken place, they have been given. So if you look back at the problem, it was given that the runoff loss in the field was 420 cubic meters. So this value of the runoff loss, that has been already given. Now the remaining one will be stored in the root zone. Therefore the water stored in the root zone, that will be the difference of these two values. And from here, if we calculate this value, that comes out to be 2460 cubic meters. Therefore this water application efficiency, that is the ratio of the water which was exactly stored in the root zone, that is 2460 cubic meter, divided by the water which was delivered onto the field. Now to calculate this ratio in percentage, we need to multiply it with 100. From here, if we solve this, we get the answer as 85.4% as the water application efficiency. Now the next one is the water storage efficiency. So if we calculate this water storage efficiency, that is represented by eta S. So this eta S, that is given as water stored in the root zone. So this we have calculated when we were doing the calculation for the water application efficiency, and it has to be divided by the water which was needed to be stored. Water needed to be stored in the root zone. That means we know that for a plant to grow completely, it requires certain amount of water in the root zone. So if we know that value, that is known as the water which is needed to be stored in the root zone. But what is the actual amount of water which has been stored? That we have already calculated. So this water which has been stored in the root zone on actual ground, that is equal to 2460 cubic meter. Now in the problem it was given that the available moisture holding capacity, that is 20 centimeter per meter depth of soil, and this irrigation was started at a moisture extraction level of 50% of the available moisture. So we will take the help of these data. Therefore the moisture holding capacity of the soil, that is given as 20 centimeter per meter depth of the soil, and in total the depth of the root zone, the effective depth of the root zone, that was given as 1.7 meter. That means the soil level is up to 1.7 meters. So for 1 meter it is 20 centimeter. For 1.7 meter depth of the root zone, this value will come out to be equal to 34 centimeter. That is the moisture holding capacity of the soil. Now it was given that the irrigation is to be started when the water level or the available moisture content is 50%. Therefore the moisture already available, that is equal to 50% of the required value, that is 34 centimeter. That means this much is already available, and therefore the moisture which is needed, that will be the remaining one. So that is 34 centimeter minus 17 centimeter, that will be equal to 17 centimeter. Now this is the depth of the moisture which is needed. Therefore the quantity of water which is needed, that will be equal to the depth into area. Only then you will be able to calculate the volume of the water. So we know the depth of the water, that is 17 centimeter. So converting that into meter, it has to be divided by 100 into the area. Now area that was given as 1.6 hectares, and if we want to convert this hectare into meter, that is the square meter units, so that is to be multiplied with 10 raised to the power for converting it into square meter. So from here if we calculate this value, that comes out to be 2720 cubic meter. But the actual amount of water stored, that we have already calculated, and that value was 2460 cubic meter. Therefore this water storage efficiency, that will be the ratio of 2460 divided by 2720. Now this ratio has to be multiplied with 100, and if we solve it further, we get the answer as almost equal to 90%, and that is the water storage efficiency for the given system. Now the last type of efficiency is the water distribution efficiency, and that is given by the relation that is eta d, that is equal to 1 minus y upon capital D into 100. Now it was given that, looking back at the problem again, so it was given that the depth of the water penetration, so it was given that the depth of the water penetration that varied linearly from 1.7 meter at the head end to 1.1 meter at the tail end. That means at one point this depth of penetration, that is 1.7 meter, at the other end this value is 1.1 meter. This is the variation. Therefore the mean depth of penetration, that is represented by capital D, that will be the average of these two values, that is 1.7 plus 1.1 by 2, that is 2.8 divided by 2. From here the capital D value, that is 1.4 meters. Therefore deviation from the mean depth, for y1 value, this will be 1.7 minus 1.4, the mod of this value, and that results in 0.3 meters. For y2 again, 1.1 minus 1.4 and mod of this value, that is again equal to 0.3 meter. Therefore average deviation, that will be equal to y1 plus y2 divided by 2, and that will again give us the value of 0.3 meters. Therefore the water distribution efficiency, that will be equal to 1 minus 0.3 divided by 1.4 into 100, and from here if we solve it, we get the value of 78.6% as the water distribution efficiency. So that's how we have calculated all the 4 types of efficiency. That completes the problem. Now in the next video we will take a look at the different irrigation requirements. Thank you.